In any situation, even the most exacting, automobile operation must be faultless. Many of the vital components which are at the base of the high performance of modern automobiles are produced in the foundry. Among these, there are some, such as crankshafts and connecting rods, which traditionally were obtained through more burdensome and expensive methods, such as forging. The necessary high qualitative level requires a constant evolution of modern production means, promptly utilizing the results of technological research in the foundry field. For casting quality improvement in particular, the knowledge of the phenomena taking place in the mold during pouring is fundamental. This film shows some techniques studied to measure these phenomena directly during pouring and solidification of actual castings. Metal motion, temperature and pressure evolution, and sound emission are subjects of fundamental interest for the foundryman. Their determination is now possible using sophisticated investigation techniques. A new instrument, the chronofluid, was developed to analyze metal motion in the cavity. It is based on electronic timing of molten metal front motion. Let us imagine placing two probes, A and B, in a mold before filling. The probes, consisting of simple electrical conductors, are connected to an electronic timer. The metal flowing into the mold comes into contact first with probe A and after a while with probe B. At this instant, the probes are short-circuited, and the electronic timer records the time required by the metal to travel from A to B. The chronofluid allows 25 timing positions. Here is the setting up of an experiment. This is a cluster consisting of 2 crankshafts and 4 disc brake calipers. To find out the filling mode of the complex mold cavities, a good number of chronofluid probes is placed in the significant locations. At the same time, also the thermocouples for temperature evolution recording are installed to visualize the solidification pattern in the different areas of the casting. An accurate positioning of all sensors is required. surfaces are coated with luting compound. After closing the flask and connecting the sensors to the instruments, filling can start. The instruments record the signals fed by the sensors. The enormous number of digital measurements, tens of thousands in a few minutes, requires their being processed by electronic computers. Processing ends with an automatic graphic presentation on charts. The interpretation of the charts reveals the pattern of the phenomena under study. The most interesting details can be visualized through suitable expedients. Let us see now how the metal fills the mold, thanks to a barrier core which, as seen in the detail, stops the main flow between the 3rd and 5th second. The thinnest parts are completed before the crankshafts. Let us see the metal entering the gate. The effect of the slag trap is also evidenced in this lateral visualization of crankshaft filling. Solidification progress, as revealed by the thermocouples, is reconstructed here at accelerated speed. The good result of a correct gating is evident. If the in-gate section is reduced, as shown in this test, shrinkage can occur on account of the premature gate solidification. Here is the setting up of a test on the water jacket core of a passenger car cylinder block. The attempt here is to combine the metallodynamic determinations with other interesting measurements: gas pressure and sound emission. To this end, tiny metal tubes are inserted in the critical points of the jacket core to read local pressures. Noises, instead, are picked up by a microphone arranged in a suitably protected location in the mold. After core installation and mold closing, connections to the pressure transducers and recorders are made. The cast iron can now be poured. Instruments are recording the data fed by sensors. Now we will see the reconstruction, on the basis of previous chronofluid tests, of a cylinder block filling with the sound emission recording of a normal pouring operation. Next comes the evolution of gas pressures in the jacket core. Pressures reach their peak about 20 seconds after pouring starts. The higher values are found in core lower portion and depend on core shape. Here we have a similar pattern. The modest pressure reduction in the upper portion does not justify the adoption of vents. A 20% increase in the core resin content does not affect sensibly the development of instant pressures. Pattern still similar to the previous one. Scarce advantage offered by vents, only in the upper region. The absence of core wall between the cylinders strongly restricts gas escape from the lower portions, whereby instant gas pressures are twice those of previous experiments. In any case, even the maximum value, about 1/10 of an atmosphere, is still amply acceptable. Here too, vent effectiveness proved modest, and the adoption of vents is not justified. With the new sophisticated measurement methods, foundry engineers can understand pouring phenomena more clearly and more easily find better solutions for the production of reliable castings.